Hi grade 11s, this is a video about the second derivative. This is day 10 in our differential calculus unit. So hopefully you've had a chance to have a look at question 1. If not, please pause the video now. So you've had a chance to think about these two curves. Both of them show functions that are increasing. In other words, as the x value increases, so does the y. But they do it in different ways. The first graph, the gradient is gradually decreasing. As we move along the x-axis, as we increase the x values, we can see that the curve gets less steep. Whereas the other one, the curve gets increasingly steep. The first curve is an example of a curve that is concave down. So that is where the gradient is decreasing. It's trying to curve downwards. And the second is a gradient which is concave up. If you trace your pen or pencil over those lines, you can kind of feel that with one you're kind of moving in towards a downwards curve, and the other you're kind of curving more upwards. And that's what a lot of this lesson is going to be about. So we're going to take a look at this function, y equals x minus 1 all cubed. So it says sketch the curve clearly showing the x-intercept. So I've already put this into my calculator. And here we are, we've got a graph. And if we go, it looks like the root is at 1 on the x-axis. Yep, there it is. Okay, so I'm going to maybe draw a little sketch out here. Okay, and this is 1. We've got our x, we've got our y, we've got the origin, and we have our y-intercept. Okay, so there's a little sketch. Find dy by dx. Now, I'm sure coming off the back of the grade 11 exam, you're all pretty well practiced with the chain rule, so I'm going to differentiate the outside function. So the outside function is our cubing. Then I'm going to multiply by the derivative of the inside. Oh, that's just 1, isn't it? So I'll just leave it like that. 3 times x minus 1 all squared. So explain from your answer to B why the curve is always increasing. So we're talking about this curve. Why is this curve always increasing? And how can we tell that it should be based on its derivative? If you like, pause the video, have a think about that. So if we take a look at this first derivative, we can see that we're squaring x minus 1. So x minus 1 could be any value, it could be negative, it could be positive, but then when we square it, we're always going to get a positive value. Multiplying it by 3 is going to keep that positive. So the slope, dy by dx, must always be positive. And if the slope's always positive, the curve is always going to increase. But you can see we've got that thing from question 1 here. With the first part of the curve here is concave down. So the slope is decreasing. And then this section is concave up. So the slope is increasing, it's getting steeper. And then somewhere in the middle, it changes over, doesn't it? So what can we say? We can say x minus 1 squared, actually let's just put the whole thing, is it always positive? Could it reach 0? It's never negative. So there is going to be one point where it reaches 0. And I guess that's going to be when, if x is 1, we'll have 1 minus 1 in parentheses. So that will give us 0. So let's say, let's rewrite this then. We can say it's greater than or equal to 0. As the slope is never negative, it will not decrease. So maybe this question isn't quite perfectly correct. It's always increasing. There is that one point where it's not increasing, where it's staying the same. But then if we think about it, if we're just before the value of 1, the x value of 1, we're going to have a positive slope. And if we're just after the x value of 1, we're going to have a positive slope as well. So yeah, this function's always increasing. So we're now going to talk about the second derivative because that was the name of the lesson. So the second derivative is obtained by differentiating the first derivative. And we have two notations. If we are doing the dy by dx notation, like we had in question 2, we would put 2's, we've got a 2 and a 2, and we say d2y by dx squared. If we're doing the function notation, remember we have f of x as our regular function, f prime of x, and then we have f double prime as the second derivative. Okay, so let's find the second derivative of this function we're talking about. Well, the first derivative's up here, so I just need to differentiate it a second time. And I'm going to use the chain rule again. So d2y by dx squared. So I need to do 6x minus 1 to the power of 1. I've reduced the power by 1. And then I multiply by the derivative of the inside. That was 1 again. Okay, so this is it. This is my second derivative. So finding second derivatives isn't more difficult than finding first derivatives. It's just doing the process again. If you wanted, you could differentiate this again and we'll get the third derivative and so on. So it's not a whole new load of techniques. State the range of values of x for which our second derivative is greater than 0 and our second derivative is less than 0. So let's have a look. I guess one way we could do this is we could graph this 6x minus 1 and we can see, let's get rid of that for now, 6x minus 1. Okay, so we want to know, when is it more than 0? Well, that is all the time it's got an x value of greater than 1. When x is greater than 1. And of course, when it's less than 0, when the y value, when we're below the x-axis, is before we get to 1. But this kind of links in with what was happening on the function, what we saw. We saw that it was concave up after 1 and concave down before 1. So it seems like there's a bit of a relationship going on here. So what the second derivative tells us about a function is it tells us how the slope is changing. Is the slope increasing or is the slope decreasing? It's like we're finding the slope of our original function. So the word we use for this is concavity. Okay, if it's concave down, it's sloping downwards. If it's concave up, it's sloping upwards. So that's the feature that tells us, that's what the second derivative tells us about. Write down the value of x which the second derivative is equal to 0. Well, there's lots of ways we could find that. We could find it here by finding the root. We could solve 6x minus 1 equals 0. But I think we've already established that it's when x equals 1. So that is the point where there is a change in concavity. It went in this graph from being concave down to concave up. And we give this a special name, this point. This is called the point of inflection. Okay, so if you were drawing this curve from the left to the right, it would be the point where when you're drawing it, you switch from curving downwards to curving upwards if you were trying to draw it in one continuous line. If you were trying to draw it in two sections, it's probably the point where you would break and start drawing again. It's our point of inflection, and it represents a change in concavity from up to down or concave down to up. I should say, add this in our notes. Change in concavity, this is called the point of inflection. You will sometimes see it written with a CT instead of an X. It's just different spellings for it. Okay, I'll leave you to have a read of this table. And I think we'll do this one example together. I'm going to leave you to have a go at the other example on your own, but I think we will do this just so we can talk about a couple of different ways of tackling it. So we've got a new function. Use your GDC to find the local maximum and minimum points on the curve. So let's x to the 4. Let's get rid of these. Okay, so hopefully you are putting this into your calculator at the same time instead of just watching me do it. And plus 2. Okay, there we go. Here's our function. Okay, kind of looks a bit like a W, doesn't it? So I'm going to try sketching this. I'm going to make sure I go up to around 2 on the y-axis, and it looks like 1 and -1 and somewhere in between. So, okay, let's just have one more look. All right. I'm trying to make it symmetrical, which I've been somewhat successful at. It's not ideal, but there we go. So we've got 1, we've got -1, and this other intersect isn't at -2, is it? And +2, so I'll do that. Okay, so we want to find the maximum and minimum points. Well, that's easy enough. We can just use our extremum function. So -1.22 and -0.25. And this one, as it's symmetrical, will be the positive 1.22 and -0.25. And we know from this that this should be 0,2. Let's just do a little X there. Okay, there are 3 maximum and minimum points. And we can see from the sketch that this is a maximum. Oh no, sorry. Let's try again. So this is a maximum. And these are both minimums or minima. If you want to be fancy and use the plural, we can say they are minima. All right, find the points of inflection. Right, so let's just think about this function. If we start on the left-hand side of the function, we are concave up. We go through the minimum and we're concave up. But by the time we get to the maximum, we must be concave down because it's curving downwards. So somewhere in here is a point of inflection. And then if we carry on, we get to the maximum that's concave down, and we get to the minimum and it's concave up. So somewhere in here, there's another point of inflection. So how can we find that? There's lots of ways we could do it. We could find the second derivative. So I would differentiate. Oh, this is an easy one to differentiate, isn't it? I could differentiate it once, and then I could differentiate it another time. 12x squared minus 6. And then if I want to find the point of inflection, I would be solving this equation because I want to find out when the second derivative is 0, when it's neither concave up or concave down. Okay, so I could do this. It is a half, and I could say x is plus or minus, the square root of a half, or root 2 over 2. Or we could, now how could we get it from our graph? There isn't a function for finding points of inflection, but what we could do is we could find the derivative of this. So remember, we type in f1 bracket x over x, and I really want to know when does the slope have a slope of 0. So I want to find the points of, I want to find the roots. Is that right? No, that's not right. I want to find when the slope has a slope of 0. So I want to find this maximum. Oh, no maximum found. That's not good, is it? Let's try again. Oh dear. Okay, this for some reason isn't working so well on my calculator. So let's think of another method. I could find the derivative of this one. So this is finding the second derivative. I've taken the original function, and then I found its derivative, and that was function 2. Now I'm finding the derivative of the derivative in function 3. Okay, so now I want to know where is this function at 0, because this is telling me where the concavity is neither up nor down. So there we go, 0.707, which is the same as the square root of a half. Let's just check. Square root of a half, 0.707. Okay, so I've spent a little bit longer on this question, just because I want to make sure that we get a bit of an idea of a couple of ways of doing this. We can think about it algebraically. And sometimes, you get questions that are written that force you to do things algebraically. They use hence a lot to make you do that. We can also do it using the calculator. All right, so let's make sure we actually answer this question. Find the points of inflection. So I've got x values. I need y values now. So I guess I'm going to need to put that value back in the original function. So I would be finding f of square root of a half, and I'll be finding f of the negative square root of a half, and I'll get my two coordinates. I'll do that in a minute. You don't need to watch me punching all that into the calculator, and I'll pop it on our OneNote. There's a little bit to read down here which talks about how we can use the second derivative just as another way of justifying maxima and minima. You probably noticed it here when we were talking about this. So I was talking about drawing this function and starting at the left of the function and travelling along it. And I said, we're concave down this whole time, and when we draw round the minimum, we're concave up the whole time. And as we draw around the minimum, we're also concave up. And then when we draw around the maximum, we're concave down. And then when we draw around the minimum, we're concave up. Whenever we draw around a minimum, we have to be concave up. It's because the minimum's the lowest point. We've got to be curving upwards. So we can use that as a way of justifying that one of these stationary points is a maximum or a minimum by finding out what value its concavity is. If the concavity is negative, you know you're going to be at one of these, If the concavity is negative, it's concave down, we've got to be at the maximum. If the concavity is positive, we've got to be concave up. We've got to be, it's got to be the lowest point, so it's got to be one of the minimums. Okay, I will fill in some answers on this example. By all means, make sure you have taken time to read through the notes that I haven't read out and think through it all, and then have a go at the last example. There will be, it'll be filled in on OneNote, so you can check once you've had a go. Good luck with it.